Thank you, Nico. And thanks to Rich and the other organizers, and also thanks so much to Susan and the great staff here. This has been a really stimulating, exciting meeting for me. And I want to start today with some broad points. I'm going to quick narrow down to a new line of research. Some of these data are like this week new, and a lot of it's the first time I've talked about this. So I'm really keen to get your input. Oops. This work is really collaborative, so I want to thank the lab, and I want to particularly give a shout out to the main perpetrators. I'll try and recognize them as they go by, but David Stewarczyk is a current postdoc in the lab. Joe Etzel is a research scientist working with me and Todd Braver. Chris Walheim's a former postdoc, and Michelle Eisenberg is a former graduate student. So for this group, I don't really need to say this first piece because this is like the Jonestown of this view. Everybody's already drunk the Kool-Aid that we build models in our head, but I want to put it in the terms that we typically use in our work, and this is from a paper with Lauren Richmond. And the way I want to put it is that cognition uses structured representations of events that we call event models to capture information about the spatial temporal framework in which activity is occurring, the entities that are present, the objects, and the other salient features of a situation. And because everybody is so rah-rah here about this idea, and I don't have to push back, I'll kind of play devil's advocate for a moment and just point out that there's this long, decades-long traditions coming from behaviorism, from Gibsonian approaches that are really critical of this heavy representation view. And so it's worth talking for a second about why to be skeptical about this. These kinds of representations are computationally super expensive. And you have to do this big nonlinear mess on the front end to get them. And so the question is why would you think that would pay off? And our argument about why it pays off is that what it allows you to do is do smoother, more close to linear predictive computations on what the consequences of your actions might be and what other things and people in your environment might want to do. So the idea is that the brain incurs this cost up front in order to get a payoff in improving predictive processing. And that's why, even though the world is sitting here representing itself perfectly nicely, we build this little model of the immediate environment in our heads. So for a long time, we've been looking in the lab at how these models of what is happening now if your immediate environment get updated, built and updated. And the basic computational framework we've developed is called event segmentation theory. And it starts from the idea that a lot of sensory and perceptual processing is predictive. This is an idea that's come up a bunch of times the last couple of days. And one insight has been that if I'm trying to predict the dynamics of my immediate environment, there's a bunch of moment-by-moment fluctuations that are noise, and I would want to have some representations that are protected from those. So that's what an event model does. It keeps track of things like where stuff is and what categories the stuff belongs to, and maybe things about people's goals and so forth. And importantly, these are representations that are in the distal variables. So this is when Josh tells us about the physics engine, about recovering the objects out there that are running the physics, and recovering the entities that are running the planning. That's super valuable because those levels are predictive in the way that the pixels and the moment-to-moment variations in the auditory signal are not. The trick is that if you're going to have a model like this, you have to update it at the right times. And so our proposal has been that you update it by monitoring how well it's working out for you. So if prediction is accurate and prediction error is low, you'll hold on to the current model. But when prediction error spikes, you're going to gate in information from the low levels of the sensory and perceptual processing stream, and also information from your general knowledge about the world, stuff you've acquired over many trials, and recent experiences that are encoded as encapsulated episodes, event memories. And it's event memories that I'm going to wind up focusing on today. There have been a couple computational implementations of this. I'm not going to have time to talk about either, but I just want to give a pointer to this paper by Nick Franklin and Sam Gershman and a couple of us that is, in my view, the kind of latest, greatest implementation of these ideas. And it does the prediction and the memory updating and the long-term memory retrieval, and it's really cool. Okay, so just a few empirical regularities that have emerged over the years that have been motivated by this way of thinking. And I'm just going to assert these, and if you want, just please ask me about them in the question period. But one thing that turns out to be true is that people agree to a kind of shocking degree about where the boundaries between events are in a continuous stream of activity. And this suggests that everybody's kind of running this architecture and updating their event models based on the same kind of rule. And you can just, if I often in these talks will show a movie and just ask people to clap when they hear a boundary, when they, experience a boundary between events, and everybody claps together with no instruction. You can do this in the lab, you can do this with stories, you can do this with comics. If you do it in a scanner and first just ask people to watch the things, they've never heard of this idea of updating event models or segmentation, and then time lock what was going on in their brain during ongoing comprehension to the points that they identify as event boundaries, you find these big phasic responses at those points that they would identify as event boundaries. Chris Baldessano and his colleagues in a really beautiful paper came out last year showed that if you just look in a bottom-up fashion at where you see abrupt changes in the pattern of cortical areas, that those correspond to people's subjective event boundaries. And they're arranged hierarchically, so there's this kind of gradient within the brain of stuff in the sensory periphery, the early stages of the sensory processing systems, tracking fine-grained events, and as it becomes more abstract and multimodal and more synapses from the retina, the durations get longer. And most critical for the proposed mechanism, we've done experiments showing that if I ask you to tell me what's going to happen in just 5 seconds, that is harder if 5 seconds is going to turn out to be in a new event. So if I ask you right before an event boundary, it's harder to predict than if I ask you in the middle of an event. And when you can successfully predict, you jack up these regions in the midbrain dopamine system that are associated with broadcasting prediction error signals to the brain. Okay, so I want to take this general framework now and focus in on memory and present a proposal that wound up being called event memory retrieval and comparison theory. The only way I can remember this is I had a D&D character when I was in middle school called Emmerich. Otherwise, I can't. And we had a better name for it, but reviewer number 2 didn't like that name. It was much more pronounceable, so Emmerich. And this kind of started from a reaction to thinking about how we study memory in human memory in psychology. So my colleague and mentor, Endel Tulving, in defining episodic memory, said that it's contingent on the establishment of a special mental set dubbed episodic retrieval mode. And I think if Endel would probably say that we've taken that part of it much too seriously. If you look at how we study memory, human memory in the psychology lab, and it's different than how we often study it in like neuroscience or in comparative psychology, but in human memory, we often act as if the system was built to take like paired associate learning tests, or more generally, to sit in an armchair and deliberately search for information about previous events. Whereas I think in and that's not, that's not what our system evolved for. In the real situation, it's much more like an automatic associative process, as has been asserted by people like Dorothy Bernstein and David Rubin. So, you're going fly fishing and you come to the stream, and when you hit that bend, you associatively retrieve information from the last time you were on that stream. And that allows you to predict things about like where your backcast is going to get hung up, where the fish might be. And most of the time, that's really good. Another thing that you probably do all the time is associatively retrieve general knowledge, stuff that you've learned about brook trout over the years. I'm not going to talk about that today. I want to focus on this adaptive role that retrieving information from recent events plays. And most of the time, the reason that you have this system is because most of the time things go the way they usually go, and so it's good to do that. But our environment does change from out from under us. So suppose you go away for a week and you come back and the stream is totally flooded and blown out, okay? So if you're me, what you do is you auto-associatively retrieve the information about the time you went fishing a week ago, and you say, okay, I still remember where those rocks are, and I'll bet the fish are there. Well, in fact, A, the fish are all over the river, or they've gone 2 miles upstream. B, the current's way too fast to do anything. And C, you take that first step and you go for an unintended swim. And that is a bummer. When you make an incorrect prediction based on that event-related information, that is a bummer in the short term. But what we want to suggest is that when that cold water goes in over your waders, that signal could be fed back to improve memory encoding so that you learn more for next time. So the basic idea is that most of the time using associatively retrieved event information to guide predictive processing is good, but when the environment changes, this can lead to prediction errors. And the key thing is that this prediction error is fed back to improving event encoding and learning. So when you experience that prediction error, you update your event model. That kind of updating is going to lead to superior encoding of that new event. And in particular, if you're lucky, what's going to happen is that updating is going to have traces of the cognitive operations of having done the episodic retrieval, having made an incorrect prediction, and then what actually happened. If you've got that, this is what Hintzman called a recursive memory representation. Then you've got information about what happened the second time, what happened the first time, the temporal relation between them, and other stuff. And that's going to be really great. And that could allow you to fend off what we classically know ought to be an interference situation, right? When we study memory in the lab, if you present, a cue like stepping up to the river with a target like catch fish, and then on another list of phrases you present stepping up to the river with a target falling into the river, you'd experience interference on a subsequent test. And so this may be able to fend off that interference and maybe even reverse it. That's what we'll see. In the lab, we're very interested, we take a lifespan approach, we're very interested in how these processes develop in childhood and then change over healthy adult development and are affected by early Alzheimer's disease. And one of the striking things in the literature on age-related memory differences are associative deficits. So Moshe Nava-Benjamin has a bunch of great demonstrations where memory for which face did I see, which rock, which fish, which bend in the river, that stuff is relatively less affected in healthy aging, but which face went with which bend in the river, those kinds of associations are hit. And this associative deficit is a lovely experiment by Chen and Nava-Benjamin, may not just be long-term. You can see it with lags as short as a couple seconds. So what this suggests is that maybe part of why people are having trouble with associations in long-term memory is that they're never binding them in working memory in their event models. And that could happen because of a basic breakdown in the mechanism of binding, or in a breakdown in the process of monitoring prediction errors or updating in response to prediction error. And so we're starting to try and suss that out. I'll give you a kind of a field report of how that's going. So what we're proposing, in short, is this perception memory cycle where you retrieve chunks of the past to predict the future. Prediction failures are bad in the short term, but they help you learn better for next time. And perception failures can spur additional processing, feeding back to enable proactive facilitation. But there's a bunch of stages where this may go south in normal aging. Okay, so now let me introduce the paradigm that we're going to stick with through the rest of the talk. And how this paradigm works is you come into the lab and we show you a movie of the day in the life of an actor. In this case, it's my colleague, Sarah Estel. And so this is about 2/3 way of the movie. The movie consists of about 50 everyday activities, and it really tells a story of a day in her life from when she gets up in the morning to when she goes to bed at night. This is from about 2/3 of the way through. She's getting home from work, and she comes home from work and walks up to the door and goes inside. So, imagine that you're a neighbor who sees her out the window, and this is what you observe. Okay. And so imagine that you're actually her stalker neighbor, and you watch her every day when she comes home. And so we show you, you watch this movie all the way through, and then we show you another movie, and we say, we're going to watch another day in the life of Sarah. And Sarah's an academic, so her life is kind of boring. Every day is kind of like the last. But sometimes things go a little differently, and she might do some slightly different things. And so you watch this movie, and she's coming home, and so there have been some things that happened on the first day. But again, she comes home, she gets out of the car, and she unlocks the door and goes inside. And you may have noticed that the second time she unlocked the door differently. The first time she unlocked the deadbolt, the second time she unlocked the doorknob. And so the idea is that for some of you, when you saw her get out of the car, you associatively retrieved this stuff about the first time she went in, and that led you to predict that she was going to do that. But in fact, what she did is this, and so then maybe you had a prediction error and formed one of these recursive representations. So people watch this movie. It's got a bunch of these items. Here's a couple other examples of the kinds of alternatives. So she might grab a white towel on day 1 and a purple towel on day 2. She might do stretches on day 1 and crunches on day 2. And you watch all this through, and we can measure various things about what you're comprehending and ask you questions about your memory afterwards. And so the first experiment I want to tell you is aimed at asking whether older adults are less likely to register these changes. And this is, I should say, this first study is from a recent paper of Chris Walheim's in JP General. And so the first thing we wanted to ask is, are older adults less likely to register these changes? And if so, to benefit from change. And the big question is basically, does registering changes in this way that we hypothesize, is that associated with better memory? So the design looks like this. You watch a day in the life. It starts with her getting up. Some point through, she comes home. A bunch of other stuff happens. And then you watch another day in the life. And on the second day, there might be items that were changed. And there might be brand new items. These are control items. And then these are repeated, clock. And then there might be items that are changed. And then we send you away for a week to get memory performance off the ceiling. And we give you a cued recall test where we ask, what happened? What kind of alarm did she wake up to? Or what kind of towel did she grab? Or what kind of lock did she open? And so the first thing to note is, and this is going to be a shocker, repetition enhances memory. So if I were showing you, like anything out of Underwood and Postman, what you'd see is that this is going to be better, and then this is the proactive interference condition. This is going to be worse, but it's not. It's better. So for the younger adults, what you see is that the changed items are actually remembered a little better than the control items. And this is totally due to those cases. So after we ask them what happened, we ask them, by the way, was that a changed item or a repeated item? And when they can tell us, oh yeah, that was changed, then they're golden. If they can't, then they're in really bad shape. The size of these balls tell you the proportions, and you can see that the younger adults, most of the time, they can tell us that it changed. If we look at the likelihood with which they intrude erroneous information from that first day, what you find is it's exactly those cases where they can't remember that it changed that they intrude the information from the first day. Now, if we look at older adults, they do a little bit worse overall. They show a pretty similar benefit to the younger adults associated with being able to recollect that it changed. But notice that here they're not seeing this proactive facilitation. And it's totally due to these proportions. So what's going on is that it's more likely that the older adults are not tracking that change. And when they don't track the change, they're less able to remember. Okay, so change can produce proactive facilitation. This is associated with encoding the change in a way that you can recollect it later. Older adults are less likely to form representations that register changes, but when they do so, they show similar memory benefits to younger adults. Another experiment from this paper shows that it's not enough to just be able to tell me at the time that it changed. It has to hit your brain in a way that you can tell me a week later that that was one that changed. So one way, so we've been basically looking at the predictive process itself 3 ways. So we're interested in these predictions during day 2. First, I'll tell you about a study using eye tracking. The second one I'll tell you about is a study where we just ask people to predict. And the third one is we're looking at pattern reinstantiation in the brain while they're trying to predict. So the eye tracking works like this. The design is pretty similar to that previous experiment. We got rid of the control items here because here we need items like the doorknob case where the 2 targets are in different locations. So that's only a subset. So we need to save them all for the eye tracking. Otherwise, it's basically the same. And what we're going to do is count up whether they were looking at the deadbolt or the doorknob in the period from between which that activity starts and when the 2 versions diverge, and then in the period from which they diverge to when her hand actually hits the target. And each of these activities is different lengths, so we've got to warp the times to get them all on the same scale. And we're looking at proportion of looking to the deadbolt, the thing that she looked at on the first day, and then the thing she's actually going to grab on the second day. And what you see is that when there's a change, with some probability, their eyes get sucked to the wrong location at the beginning of that event. And then it diverges, and eventually they get to the target, but in the change condition, they get there a little bit more slowly. So they're less likely to get there early, they're more likely to get there late. If making this error, this predictive error, is leading to a set of processes that facilitate better memory encoding, then if we just zoom in on the changed items and backsort based on whether they could later tell us that it changed, it ought to be those trials in which they make that predictive error that they're later able to tell us that it changed. And that's, in fact, what you see. So in those conditions where they can recollect the change, they remember more. OK, so viewers' predictive eye movements are guided by recent events, and when things change, people make prediction errors. And these prediction errors are associated with better subsequent recollection of the change, which is a kind of neat paradox. To look at age differences, I want to show you data from this explicit prediction task and then one more experiment. So in the explicit prediction paradigm, what we do is we split up the day 1 movie a little bit. And I did this reluctantly because I'm always reluctant to kind of break the normal event comprehension mechanisms. And in real life, we don't see like little commercial breaks between the actions. But we needed to do that because on the second day, we wanted to ask them to predict what was going to happen next. And we wanted them to understand what we meant by next. Like, so we could say, predict what happened until the next break. Whereas if we say, ask what might happen next, they might say, well, I think she's going to get her PhD and move down to North Carolina. OK, so this is an example of what that looks like. So she unfolds the yoga mat. We ask what's going to happen next. And then we show them. And so in this case, she sits down and does stretches, I think. Nope, crunches. So much for my episodic memory. OK, and so what we're interested in is the predictions they make in the relationship to later memory. So this is just showing you a lovely replication of that first experiment. So basically, you get repetition enhancement, and then, repeated items are better than changed, but you get proactive facilitation when they recollect, and older adults are less likely to do that, and they show more of a hit than younger adults going from repeated to changed. So now what we're going to do is we're going to backsort based on whether during day 2, when we stopped and asked them to predict, they made a prediction that was consistent with what they should predict if they remembered what happened on day 1. And so for the younger adults, what you see is that when they make that, so these are changed items. So this prediction is about to be shown to be in error, right? But it's the prediction you ought to make if you're predicting based on what happened on the first day. And so the younger adults, they remember more under those conditions. The older adults, there's two really interesting things. One is they have poor encoding of that first day, which isn't that surprising. And that's evidenced by the fact that the green ball is smaller for the older adults than the younger adults. But even when they do make a prediction that's based on their memory that's going to lead to a prediction error, they don't show this memory boost, suggesting that they're going ahead and predicting this thing that's then not what's going to happen, and then breezing right through breezing right through that prediction error signal. And consistent with that, what you see is that making this thing that's going to lead to a prediction error, instead of leading to proactive facilitation, here it's making them more prone to intruding what happened on day one, or it's associated with being more prone to intruding what happened on day one. So the older adults make fewer memory-based predictions. Even when they do so, this is associated with less of a benefit to their subsequent memory. And these elevated false alarms suggest that the prediction errors being the predictions being misencoded as part of what actually happened on day two. Okay, so this last study, I mean, we literally got these initial analyses this week, and so this is like very much work in progress, and I don't have the whole story traced through from memory and statement to prediction error to subsequent memory. But I do want to tell you about it. I'm very keen to get input. So this is a functional imaging study in which we're scanning the encoding period and then sending them away for 3 days and then testing their memory with the cued recall test. They're doing this prediction test that I just showed you in the scanner. And so what we're interested in is what happens when your brain hits these changes, and more importantly, what happens when you're lying there trying to predict what's going to happen next using your memory, and how is that related to your subsequent memory. So the larger hypothesis is that reinstating what happened when you were encoding that activity on day one and using that to guide your predictions is going to be associated with a larger prediction error response when we change things on you, which in turn is going to be associated with better subsequent memory. So we don't have all of that chain analyzed yet. But what I can show you is that the brain gets freaked out when you hit changes. So there's a lot of areas that show mass univariate increases and decreases in default mode areas when you encounter a change in the event. So this is time locked to the onset of that change after you made your prediction. And a subset of these areas, including, so you can see the hottest spot here is here in the medial temporal lobes bilaterally. Doesn't show up, it's not rendered so great on the surface, but here in these slices, what I'm showing you is in a subsequent memory analysis where we ask, how much does the magnitude of that evoked response correlate with the likelihood that you're going to remember that event later? And so the hippocampus shows a nice subsequent memory effect for these surprising changes. Okay. But the main analyses of interest are pattern analyses of the sort that you've heard about a couple times today. So the way this works is for each parcel that we look at in the cortex, you get the spatial pattern while people are watching the end of an activity on day one. And then while they're predicting how that activity is going to end on day two. So this is before they actually see what's going to happen. And then so what we're going to do is correlate the pattern while they're watching the end of day one to the pattern while they're predicting what's going to happen on day two. And to the extent that you're seeing red on the diagonal, this is an area that shows a pattern that's more similar to what they experienced on day one when they're predicting that same activity than when they're predicting the prediction, here's the right way to say it. The prediction on day two, the pattern that evokes, is more similar to the pattern that they encoded when they watched on day one for that activity compared to the other activities that they saw, which are on the off diagonal. Now you can also see this kind of block structure, which reflects the fact that there's larger temporal structure in the activity. So she gets up and does a bunch of things in her bedroom and then moves to another room and does some things there and then leaves the house and goes to work and does some things there. And that structure is also reflected here. Okay. So the measure of reinstatement that we're going to be using is the magnitude of these on-diagonal correlations minus the magnitude of the off-diagonal correlations. And we're going to rinse and repeat this analysis for 300 parcels that were derived from functional connectivity in another data set by Thomas Yo's lab. And those 300 parcels group into these 17 networks. And I want to focus your attention now on these three subcomponents of the default mode network in the posterior and anterior medial cortex, and here in the lateral parietal cortex. And we also used some hand-traced hippocampal ROIs because the hippocampus isn't in the Schaefer atlas here. And so I'm going to show you magnitudes of this reinstatement effect, the on-diagonal correlations while you're predicting minus the off-diagonal correlations. First, to just show the magnitude of reinstatement, which to my surprise is substantial, like in lots and lots of the brain. So most of the brain, 0 is no more similarity to the thing that you're predicting based on compared to the other things that you saw. And kind of the whole brain shows these reinstatement effects, which I found a little bit surprising. Now what we're going to do is we're going to ask whether the degree of that reinstatement is correlated with the degree to which you made a memory-based prediction right before, the degree to which you made a memory-based prediction right after we recorded this brain activity. So you're sitting there thinking about what's going to happen. We ask you what you think is going to happen. To what extent does the reinstatement predict your behavioral memory-based predictions? And so these are much lower and much more selective. But if you look in those default regions, what you see is pretty robust association between this cortical reinstatement and the behavioral index of prediction, particularly in the left hemisphere for reasons which are mysterious to me at this point. Okay, so change drives in this paradigm a neural orienting response. And in the anterior hippocampus, this is associated with subsequent remembering. Repeated event features drive neural reinstatement, and that's associated with this. I said subsequent remembering, but it's subsequent remembering in the context of predicting. And so the questions going forward are, does that reinstatement effect predict how surprised you are when we show you the change? And does that in turn predict your final memory for what happened on the second day? And then are there age differences in any of this? So this study involved a few dozen younger and then a few dozen older adults. I'm showing you just data from the younger adults. Okay, so to back things out a little bit, during comprehension, we build models of the immediate environment to provide predictive guidance for our comprehension. And associative retrieval of event memories informs these models. When things change, this leads to prediction errors, which is a bummer in the short term, but can drive a more robust integrated memory representation that we can learn from in the long term. Older adults are less able to take advantage of these prediction errors to benefit encoding. And the name of the game at this point with the aging is to understand where in this cascade things are going south. The ability to do this kind of reinstatement is associated with this kind of predictive processing is associated with pattern reinstatement during change encoding. And so I'll stop there and take a few questions. And thank you.
Very interesting.